Hello and welcome to our short video on the factors affecting sensory receptor response properties. So when we look at our sensory receptors, we're talking about receptors such as proprioceptors, touch receptors, pain and temperature receptors, and then our C fibers, which are also for pain, temperature, and itch. So basically, when we think about our sensory receptors in our schematic, we're talking about the box down here, and they bring in the information to the central nervous system, in particular the spinal cord, before it is then passed up to higher centers or the sensory motor cortex. So all of these different weird and wonderful receptors, of which there are sub-classifications or subtypes, I should say, they bring that information in. So when we talk about these receptors, there are three factors that affect their response properties. So three things that affect the way they respond and affect basically the information that gets to the sensory motor cortex. So as you can see here, we have sensory functions, receptor types, afferent axon types, diameter, and then conduction velocity. And so the first thing that we want to talk about is our axon diameter. And the basic rule is that larger sensory afferent fibers, axons, propagate a lot faster. And as you can see here, 80 to 100 meters per second for our larger axon diameters, which are our proprioceptors, or in particular type 1A, which are our muscle spindles. So muscle spindles are our largest fibers, so they fire the fastest because their axon diameter is the largest, towards 20 micrometers in diameter, and therefore the fastest, around that 120 meters per second. If we look at then our touch receptors, Merkel's, Meissner's, Pacini, and Ruffini, they're known as an A beta fiber, and so they're the second classification down. You'll notice it's a smaller axon diameter, and therefore because of that smaller axon diameter, there's a slower conduction velocity within that axon when that fires off, 35 to 75 meters. And then finally you get to your delta fibers, A delta fibers, which are pain and temperature. They're much smaller again and much slower, therefore. And then you're unmyelinated, so all three of those ones are myelinated. The unmyelinated and smallest of all, C fibers, which are our free nerve endings, are very slow, 0.5 to 2 meters per second. So that's the first property that we can talk about that has an effect on the sensory responses. So the speed of action conduction velocity, action potential conduction velocity, is in part determined by axon diameter. The second part is our size of our receptive fields. So the skin surface basically has, and what we're talking about here primarily are our touch receptors and our pain temperature, not so much our proprioceptors, because they're much deeper, obviously, in the muscle and tendons themselves and joints. But if we're talking about our touch, pain, temperature receptors, the size of the receptive field. So basically on the skin, there's areas of which stimulation will cause some sort of depolarization of a touch receptor. And so the size of the receptive field is largely a function of the branching characteristics of the afferents within the skin. And so where there are small receptive fields, so they're over in here in the fingertips, then we have a sort of a faster conduction velocity. And that's because those smaller fields are less likely to be influenced by each other. Whereas when we get to our larger fields, our 2-point discrimination here in the forearm, what we have are our what's known as sort of like lateral inhibition within the surface of the skin. And so it becomes an issue if we look at red here, where if we have too many overlapping large receptive fields, what can actually happen is we get a muddying of the waters, and that's because the behavior of one receptive field or a neighboring receptive field can influence the other. So it can actually then inhibit the neighbor, in essence. And the other thing that we can talk about is the temporal dynamics of the sensory responses. So this refers to the rate at which sensory receptor endings adapt to a given stimulus. So you can see here that we have a stimulus, and that might be putting pressure on the fingertip. So we turn the stimulus on by putting pressure on the skin surface. There's two different ways a receptor can behave. We can have slowly adapting receptors. Basically, they're firing. Each line is a firing of an action potential. In this case, we can see that it's firing fast to start with, and then it slows down slowly. So that's a slowly adapting. So it's going bang, 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 bang. Essentially, like it's saying, is that it slowly adapts its firing rate when there is a stimulus applied. If we talk about rapidly adapting receptors, basically they only fire when there is a change. So we put that sensation on, we put that pressure on the finger, it goes bang, 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 but then quickly or rapidly identifies that stimulus hasn't changed. If I was to then take that stimulus off, so if you imagine that the stimulus then came off and it went flat, rapidly adapting would fire really quick when the stimulus went on, turn off, and then fire again really rapidly when it was turned off, but then adapt quite rapidly again. So they're kind of phasic. They go bang, 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 bang. Something's changed. Okay, now it's constant. Turn off. Bang, 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 bang. Something's changed. So rapidly adapting. And so another influencing factor when we talk about those receptive field sizes and adaptation rates is the location in the epidermis-dermis sort of areas. In particular, when we talk about our Meissners and our Merkels, we can see that they're quite close to the surface of the skin. They're the ones that have very small receptive fields. But one of them is rapidly adapting, and that's Meissners. One is slowly adapting, Merkels. Whereas deeper in the dermis and subcutaneous levels, we have our Ruffini's and our Pacinian. And again, these ones are larger, so they're a bit slower to fire off, remembering that our firing rate of larger receptive fields is a bit slower. But we also, within those larger receptive field types, we have both a rapidly adapting, a Pacinian, and a slowly adapting Ruffini's. Now, what that does is basically tells us or allows us to sense any kind of change, those rapidly adapting. So if there's anything changing in the environment that's in contact with us, or with slowly adapting, allowing us to understand what is constantly stimulating us. Basically, all of that in a nutshell is an explanation of our sensory receptors' behavior when being stimulated. The factors that will affect the conduction velocity, the factors that will affect the behavior of the firing frequency are all to do with those three factors that I just talked about, plus other sub-factors such as a location within the epidermis, dermis, and subcutaneous layers. Thanks for listening, and talk to you soon.